Okay, Assalamualaikum and hello guys. My name is Muhammad Hazman bin Muhammad Usnin. My metric number is 198554. Okay, today I will talk about the pressure reduction. Okay, for the pressure reduction, the molar flow rate inlet is 292.9 km per hour, and the outlet also same as the inlet. Okay, the mole also same for the every unit. Okay, the purpose that we put the pressure reduction is to reduce the pressure of the components. Okay, first, the pressure reduction is the non-reactive unit. So to calculate the heat, to calculate the Q, I just use the simple calculation, like choose the reference, that this reference, I take the inlet as a reference, and then the I take the the table B2, the value on the table B2 for the A B C D for the every substance, and then use the formula Q equal to uh, mole flow rate times to the times to the heat, and then outlet minus inlet, and then the Q that we get is 764.7506 kilowatt. Okay, the next BFD is heat exchanger. Okay, the mole still same, inlet and outlet, because this is the non-reactive unit. So we just calculate as the same. Okay, the purpose that we put the heat exchanger is to increase the temperature of the feed, because the temperature from the pressure reduction is 250.35 degrees Celsius, and then we have to increase this temperature to the 300 degrees Celsius. So also calculate using the same thing, like first I choose the reference, the inlet reference, the inlet as a reference, and then the table B2 for the every substance, and then A B C D, and then calculate the Q. The Q that I get is 199.4580 kilowatt. Okay, and then the outlet from the heat exchanger will go into the OCM reactor. Okay, before that, this ASU unit. The ASU unit also will go to the OCM reactor. Okay, first, for the ASU, I calculate using the Bernoulli the mechanical equation. Like we calculate on the W work shaft, and then after get the work shaft, W equal to Q, and then the Q is 1711 kilowatt. Okay, as the same, the ASU also we have to choose the reference. So I choose the inlet as a reference. That's why the W1 have a value, because this O2 25 bar will minus with the 1.01 bar, so this have a value. For the work shaft 2, is not have the value, because it's same as the inlet. The value is same as the inlet, so it's a 0 kilowatt. Same as the work shaft 3 and work shaft 4. Okay, and then I total up it. Okay, the purpose to do the ASU is to obtain fresh oxygen input, because in our reaction we want to we want the oxygen, the higher mole of oxygen and lower mole of nitrogen. Okay, after that, the OCM reactor. Okay, the purpose we put the OCM reactor is to crack methane to ethylene. Okay, the OCM reactor, the temperature inlet is 300 degrees Celsius, and 6 bar. The pressure is the same inlet and outlet, but the temperature increased to 800 degrees Celsius. Okay, for the OCM, this is the reactive unit. So, for the reactive unit, I calculate using the heat of formation method. Okay, first, the reference is fixed, C, carbon, solid 35 degrees Celsius per atm, hydrogen vapor 35 degrees Celsius per atm, O2 vapor 35 degrees Celsius per atm, and nitrogen vapor 35 degrees Celsius per atm. Okay, when this is fixed, so I have to calculate the inlet and outlet because the inlet is 300 degrees Celsius and the outlet is 800 degrees Celsius. So it's the same. I take the data from the table B2 for the every unit and then A, B, C, D, and then calculate it as usual. Q equal to NH out minus NH in, and then the Q I get 1399.9 kilowatt. Okay, for this heat of formation, we have to plus with the heat of formation that can get from the table B1. Okay, so this is the final answer for the Q. Okay, that's all from me. Thank you.
Hello doctor, my name is Pavanisha Vikraman and my matrix number is 195859, and today I will be presenting about my unit, which is the cooler. The cooler has one inlet stream and one outlet stream, and the molar flow rate that enters the stream is exactly the same as the one that exits the stream. And the cooler is right after the OCM reactor and before amine CO2 absorber. The inlet stream's temperature and pressure is 800 degrees Celsius and 6 bar respectively. And for the outlet stream, the temperature is 40 degrees Celsius and the pressure is 11 bar. So basically we can see that the temperature is reducing and the pressure increases very slightly. And we have to calculate the H value for each component, and our reference point is 800 degrees Celsius, vapor phase and 6 bar. Oh, and the components that are entering the stream and exiting the stream are all in vapor phase. So since our reference point is 800 degrees Celsius and 6 bar, which is our inlet stream, so our H values for our inlet stream will all be zeros. And so we have to calculate the H value for the outlet streams only. And the H value is calculated for each component. And then to find the value of Q, we have to multiply the value of molar flow rate and H for each component, and then you have to sum it all up to get the Q value. Basically, the formula to find Q is the molar flow rate times H for the outlet stream minus the inlet stream. But then since the inlet stream is all zero, so we just sum up the multiplication of molar flow rate and H for each component, and that's how we get the Q, which is 4,598.1 kilowatt.
Assalamualaikum and hi, my name is Nur Shafika binti Julian and my matrix number is 198935. So today I'm going to present about my unit, which is acid gas removal unit, or also known as amine CO2 absorber. The purpose of this unit is to remove maximum concentration of carbon dioxide gas. So here is how I'm going to calculate it. this slide, for this presentation, I'm going to explain how I did for my energy balance. Firstly, the inlet stream for this calculation, which is this inlet stream, I have inlet and outlet stream, which is prior to the energy balance calculation. So these M8, M9, M10, and M12 are those that are used to calculate the energy balance, the heat that released or absorbed into the unit. So from here, it is at 40 degrees Celsius and 11 bar. Same it goes to here, but the outlet stream here is 30 degrees Celsius and 35 bar. And lastly here, 41 degrees Celsius, 41.3 degrees Celsius and 11 bar. Okay. All these units, all these components are in gas phase, except for M9. So these M9 at M9 and M12 are in liquid phase. So in this case, to simplify my calculation, to make it easier, I make the inlet stream, the pressure and temperature of inlet stream, as the reference state, and including the M9 here, the temperature and pressure of M9 liquid M9 here, also the reference state. So due to that, I will obtain zero change of pH in the inlet stream. And except for amine, I have I calculated it, and I got negative 43.1230 is due to the change of temperature and also the change of phase. Okay, for outlet stream consists of M2, M12, and M10. So M10 I calculated by the C sub VDT, but I just because the change of pressure in phase in gas phase does not yield any enthalpy. Hence, I only do the calculation on temperature. So using the normal calculation, and I will get this much. Okay, so to find the Q, the heat released by the plant by the unit is by multiplying N by the sum of multiplication of flow rate of outlet flow rate and the H of outlet stream, minus with the multiplication of flow rate in the inlet and with the H of in the inlet. Hence, I will get this 1330.77 kilowatt.
Now let's look at the demethanizer unit. The purpose of demethanizer is to separate ethane and ethylene from the main stream. If you look here, demethanizer has one input and two outlet streams. In the inlet stream is coming from the CO2 absorber, while this stream, it goes to the compressor, and this stream is removed from the unit and the system. Alright, the inlet streams are all in vapor phases, while the outlet stream, it has two. So the top one goes out as vapor phase and the bottom one goes out as liquid phase. And for the inlet stream, the temperature and pressure is 30 degrees Celsius and 34.75 bar respectively. And for the outlet stream, which is going out as vapor phase and liquid phase, both of the temperature and pressure is 200 degrees Celsius and the pressure is 34.75 bar. Alright, and the reference to find the H value, the reference is kept as vapor phase, 30 degrees Celsius and 34.75 bar. To find the Q value, the value of N is multiplied with H and and sum up all the multiplication value to find the value of Q. And the CP value for liquid is obtained in the internet. Thank you.
Assalamu alaikum. Hello, doctors. My name is Ahmed Jamal Amoudi. I'm doing right now. My matrix number is 191491. I'm doing here video for energy balance. Our project is about producing ethylene out of shale gas. So I am from group 2. Let's start. So here on my part we have compressor. The compressor, the idea of compressor is to increase the pressure. So we need our our product to be in certain pressure. So for that to become at that pressure, we needed a compressor for it. So our previous pressure is 34.75, and the pressure that we need is 35.3. So for that we added a compressor unit to do so. So we have our feed 39.7 kilomole, and the output is the same, 39.7 kilomole. The idea of material balance is basically input equals output. As you can see, there's no changing in the values of the mole fraction of ethylene or ethane, the one that comes from demethanizer, or as an output to go to C2 splitter. Input equals output, non-reactive system. So this is for material balance, but I need to mention that our compressor is isothermic, or in other words endothermic, which means the temperature is the same for the input and output, or should I say are constant at 30 Celsius degree, no changing. Let's continue for the energy balance. Since it's endothermic or isothermic, we can calculate it through different ways. One way is basically delta P times the specific volume, or another way we can do the mechanical equation here, which is delta P over the density equals the work shaft over the mass flow rate. So basically we have four parameters. The first parameter, which is delta P, you can get it from 35 output minus the 34 input, and we have 0.55. We need to change it to Newton over meter square. So so we have right now 55,000 Newton over meter square. So now we got the second parameter, which is the mass flow rate. We just change the mole flow rate that we have times we just change each one we just change we times the mole fraction times the mole flow rate, and then we times it with the molecular weight to get the mass flow rate, and then we add them all together to have the mass total flow rate. And we have the density. Basically the density are the addition of both species. The species are ethylene and ethane. So now calculate this mathematically. Therefore we have the work shaft, we have everything here, which is the pressure, the difference in pressure times the mass flow rate over the density, and we got it here Newton meter over per hour. So right now we just need to change the units from Newton to kilojoule per hour, and then we change it to kilojoule per second, and finally, since it's kilojoule per second, which means it's kilowatt. I just need to mention again that the purpose of this compressor is basically to increase the component pressure or yeah, that's basically the idea of our compressor. After our compressor, the unit compressor, we just go to the C2 splitter. Here in our C2 splitter, I just put myself down here, right? So in C2 splitter, we have one input, one feed that comes from the compressor, and we have two outputs. I just need to mention that the feed is in liquid state already. Actually, it's from liquids from the demetanizer already. So now this is now we have the C2 splitter. Uh, the feed is coming from compressor, and we have two outputs on the top and on the bottom. So in the top, we have the one that it's desired, the one with high purity, the one that we need in liquid state, actually, ethylene, our product, with temperature of 269, and the feed, we just need to mention that the feed is 30 Celsius degree, which means it's 303 Kelvin. So now, to calculate the energy balance, since there is difference in the temperature, we only have one way to calculate it, which is by the enthalpy, or in other words, to be specific, by the CVDT. So after getting the reference, all the species at liquid states, 303 Kelvin and 35.3 bar. So we can get the table for ethylene and ethane, and you can see here that the enthalpy for the input are zeros because it's from our reference. We started from there, so it's zeros. However, in our outputs, it's quite different because we have difference in the temperature. We just need, and you just need to mention that in C2 splitter there's slow pressure drop. However, through my journal, it's been neglected, so we assume that the pressure is constant. So now, as we say, to continue our calculation in C2 splitter, we're going to use the CVDT. So we need some data. We can get this data from table B2 for ethylene and ethane. Basically, these data for the CB, or the heat capacity, for A and B and C and D. And there is an equation, as you can see in the third, in the middle of in the right, the CB equal the integration and so on. So as I said before, that the enthalpy H1 and H2 are zeros. Why? Because we start from our reference. So we have to calculate only H3 and H4. After that, we're gonna times it. After we get the enthalpy, we're gonna times it with the mole flow rate. That's then we're gonna calculate the Q by the summation of the output minus the summation of the input, and therefore we have minus 41 kilowatt, 0.1 kilowatt. Again, the purpose of our C2 splitter is basically to increase or to produce a high purity of ethylene. That's basically our C2 splitter, our final unit in our design. Thank you so much, doctors, Dr. Rosita and Dr. Dean. Thank you so much. Have a great day.
Now let's look at the costing. Alright, the price of feed and product is obtained in the internet. Okay, now let's look at the highest value and lowest value for feed and product is found in the internet. So the highest value of shale gas and MEA is as written here, and the lowest price for shale gas and MEA is also written here. And as for the price of product, it's per year, Ringgit Malaysia per year. The highest value and lowest value is obtained. but in the internet we found in USD per year. So we converted it by multiplying the value with 4.17, which is the conversion rate of USD to Ringgit Malaysia for this current economic state. And so the price of ethylene per year is this, and then the price per kilogram is also calculated, the highest value and the lowest value. The average is when we plus the highest and lowest and then divide it by 2 to get the average value. And also we calculated the RM per MMT value, highest and lowest as well, for the product which is ethylene. The fixed capital costing is also calculated for each unit. We calculated the Q value, which is hit in the previous slides. So for each unit we calculated the value of Q and the cost per year, and the electricity cost is also obtained in the internet as well, and it's per year, it's Ringgit Malaysia per year, and we calculated for each unit. And so this is the total of the electricity cost for every unit, and over here we have the price of each unit, and this is the total price of all of the units. And over here we have the electricity price in USD. So we converted the USD to Ringgit Malaysia because that is the currency we are using in Malaysia. So in order to convert USD to Ringgit Malaysia, we multiply it with 4.17, which is the current currency rate. Over here we have ISBL plus OSBL. We have the land, and the land is 38,000 square feet, and the price for it is 100 ringgit per square feet. And this is the electricity price which we calculated in the previous slide. And this is the price for total units for waste treatment, and this is the total for ISBL and OSBL. And for the engineering and construction, it's 0.3 of this value. And as for the contingency, it's 0.1 of this value. Then we have to total up this, this, and this. For the working capital, we calculated the funds and the reactant value. The reactant is shale gas and MEA, and for the funds is the startup and raw materials that is needed. The funds is 0.2 of the capital cost. And for the variable cost, we have shale gas, MEA, which is the reactant, and then we have electricity, land, and waste treatment prices over here. And then the fixed cost is the cost that is fixed, which is the maintenance, where we have to maintain the units so that they are functioning, the flow would be correct. And then the labor for the workers, this is the price. And the overall cost is where is the sum of variable costs and fixed costs. For tax and depreciation, the total equipment cost for all the units is this, and then the depreciation we used 5% per year, which is 0.5 times this value. And the cost analysis is where we minus the total, is where total minus the depreciation, and then the tax is 18%. And then for the next tax calculation is ISBL and OSBL. The same thing, where we have the depreciation, and the cost analysis is total minus depreciation. For the tax, we have 18% and 24% because the total ISBL and OSBL is a lot. So the first 18%, the tax for 18% is for the first 5 million. And then the following 24% is for the following values. The next tax calculation is for total investment required, which is the working capital. And then we have the depreciation. The cost analysis is total minus depreciation. Then we have the tax. 18% is for the first 5 million and 24% is for the following values. Alright, and for the risk analysis, we have lower price and higher price. For now, we neglect the average price. We have the feed and product, and over here we have the profit we gain if we vary the price of feed and product. Over here we have low feed price and low product price, which both are low. Over here we have both when both are high. So looking at this, our profit would be in positive value if our feed and product price, if our feed price is low and our product price is high, or when our feed price is high and so is our product price. Yeah, that's it for the costing section. Thank you. Oh, and over here we have this is profit in Ringgit Malaysia. Profit in Ringgit Malaysia, and over here is the profit in percentage. And it's clearly it's in positive value when feed price is low and the product price is high, and if the feed and product price is high. That's it for costing. Thank you.
So, in conclusion, by feeding 4751.59 kg per hour of shale gas to the plant, our company can produce as much as 1003.42 kg of pure ethylene in a year. Based on the costing calculation, it is found that the company will gain high profit if the raw material is bought at lower price while ethylene product is sold at higher price. It is shown at the presentation of costing done by Pava. As for the recommendation, during the shale gas ongoing this method, there are waste gas and impurities of ethylene. These wastes should be handled for the environment's safety. The calculation for this costing is just an estimation of profit, as the capital cost does not require the actual expense on the plant, such as transportation fee and many others.